Hello everyone and welcome to this video on a review of the XMOS multi-core StartKit. XMOS is a fabless chip company and they make quite an interesting series of chips that, in my opinion, fit some sort of niche between FPGAs and, let's say, ordinary microcontrollers. You can get these chips starting at $5 in single quantity, but depending on the number of cores, whether you want to have an onboard ADC and things like USB, the price starts to rise. In any case, you can get various chips in TQFP, QFN or BGA packages. I actually ordered a bunch of them in the TQFP package because I think that's interesting because soldering a QFN is a bit of a pain in my opinion, and soldering a BGA is a massive pain, so it's nice to have these, or at least some of these chips available in TQFP packages. If you don't want to go directly with the bare chip, you can also buy this StartKit for about $15 on DigiKey. And the reason I have two of them is that some time ago they had this, they called it a StartKit drawer, which was basically you could submit an idea for a project, and then they would kind of gauge that, and if they deemed this to be sufficiently interesting, they sent you a free StartKit. So I did that, and I said I wanted to do some DSP on these guys, and they sent me one. And then I started to play around with it, and I actually really liked what I saw, so I decided to buy a second one to be a little bit more independent and not have to destroy my setup and set up everything else for another project if I wanted to work on several projects simultaneously. Anyway, I decided to make this a series of videos, so the first video will be the one you're watching right now, and that will consist of a brief board overview and then a discussion of what is special about these chips and why they are interesting and what kind of applications they fit. And I'll also talk a little bit about the documentation and the IDE, and the second video will actually be a small hands-on project. Most likely this will be I have this LED strip here that actually comes on a reel. It was fairly expensive, I think around $60, but it's got RGB LEDs, 3 RGB LEDs per segment that are driven with one of these WS2811 driver chips that allow you to address each RGB LED individually. And my plan for this is to put them on my bookshelf and to have some light effects there. And when I started this project, I was using an FPGA to do this. And then I realized that these XMOS chips actually would be quite nice to do the job instead of an FPGA. So most likely I'm going to demonstrate how I'm planning to pull this off. Okay, so let's have a quick look at the board. This is what you get when you order it from DigiKey. It's also what I got when I got it from XMOS themselves. This comes in both cases inside this box that you saw previously. It's got like some nice foam inside, but as you notice, you actually have to put in, you have to solder in the headers yourself. Which I did on one board but not yet on the other one. But anyway, so you just have to be aware of that. You have to do some very mild soldering in order to use these GPIO ports. Here, of course, is the main XMOS chip that is powered by a 24 MHz crystal. Although this guy has a PLL inside, so it's actually not running at 24 MHz. But I'm not really sure whether this is variable or not, but in any case you can set this to a much faster clock rate than 24 MHz. There is an ADC port down here that more or less goes straight to the built-in ADC of the XMOS chip. And there is a micro USB connector here that you can use for programming, for debugging. In case you're wondering, this not populated footprint over here is, according to the schematic, is one of these clamping diodes / TVS diode transient suppression chips that they decided not to populate for whatever reason. these parts over here are inductors that are used for the built-in DC to DC converter, and there is a 3.3 volt low dropout regulator over here. So this is a dual channel LDO. One channel is used to power the ADC section of the chip, and if I remember correctly, the other channel is routed out to this header over there. So you can use these 3.3 volts, although according to the datasheet, this chip only is able to give you, only, whatever, it's giving you 300 milliamps. So you have to be aware of that, and ideally not draw more than 300 milliamps from this port. In general, the chip, when you run the demo program that they have put pre-programmed, the chip actually gets fairly hot. According to the specifications, it's supposed to dissipate around 600 milliwatts. Of course, that always depends a little bit on the program, but I measured the current draw from the USB port, and it's more than 100 milliamps. Granted that they're powering quite a bunch of LEDs, but still, the current consumption was a bit higher than what I would have anticipated, so this is something else to be aware of. They have a SPI flash chip over here. When you use this thing, you can either program it directly via USB or write a program into the flash, and then you don't have to program every time when you power up the board. So anyway, that's nice. There's a bunch of LEDs over here, 2 LEDs here, 9 LEDs here, together with the current limiting resistors up here. And these LEDs are actually shared with some of the ports that we'll talk about later. Then there's a push button, and they also have these capacitive sense pads here. Now, honestly, on an evaluation board, I never really found much use for these. But anyway, if you want to play around with that, and they put it on the board, and they also have some demo programs on how to use these. In terms of connectors, there is one populated connector up here, which is a PCIe connector, and you can use this to plug in sort of extension cards that you can get from XMOS with DACs and other kind of just peripherals that you can plug in here. This port is shared with this GPIO port down here. And there's 2 more ports here and here. This is a 2-row port. It's supposed to be compatible with a Raspberry Pi, but I'm not really sure what that means. But in any case, and there's yet another port up here that allows you to do even more GPIO, as well as something called XMOS Link, I think, which is a way of connecting several of these chips together using a high-speed bus. And this is quite useful because some of the applications for this chip are actually taking several of these and sort of using them together. And there, of course, it makes much sense to have a fast connection, a standardized connection between these chips. And they also give you software support for that. So this is clearly a very handy feature. Okay, that's it. Oh no, I actually wanted also to mention that every pin has a nice silk screen label. Now, as I will show next, using these pins and ports is a bit, in my opinion, is a bit convoluted. So having these labels on the silk screen certainly helps a lot, because even though it's printed quite small, at least you don't have to check yet another reference sheet, but you can just read on the board what pin you're dealing with. And on the back of the PCB, this is just to prevent reflections on the camera here. On the back of the PCB, they give you even more pinouts here. And you can also see that you have these, this is called LNK0, LNKC, LNKD, if I turn it around correctly. And this is this XMOS link I was talking about before. And also they give you the pinout for the Raspberry Pi connector here. Okay, that's it for the board. So next we'll discuss what makes this chip special and what kind of cool applications you could build up with it. The 2 features of the XMOS microcontroller that stand out in my opinion are its ability to do flexible I/O and its ability to do several things in parallel due to its multi-core nature. These two features make most sense if you consider them in parallel, although I of course have to present them sequentially. And I'll start with flexible I/O. On this sheet of paper I have printed out the block diagram of the architecture of an Atmega 328P microcontroller. This is a microcontroller that you will find on some Arduino boards. There is a main CPU here and quite a bunch of peripheral modules, such as in particular a serial COM hardware peripheral, an SPI peripheral, and an I2C peripheral. These peripherals are very handy if you want to do, let's say, serial communication. Then first you set up the module, and then you use the CPU to tell this module that you want to send off a byte. But when you've done that, the hardware module itself takes care of doing that. And on the main CPU, you can continue with other code. Maybe you have some calculations to do or some other things. So the main point is you don't have to wait for this I/O to complete. You just send it off to the hardware peripheral and this module does it on its own. Now, there is instances where you want to use something else for communication than serial SPI or I2C. For example, maybe you want to talk to an LCD display, an Ethernet controller, or whatever. In that case, what you really should do if you're working with such an architecture is getting a microcontroller that actually supports that hardware. But sometimes you cannot do that. For example, in the case of this LED strip that I showed before, there is really the protocol that you need to talk to this thing is quite unique. So you're not going to find a microcontroller that supports that protocol, which means that you have to do it in software. So what I'm going to do next is I will first show how you would use this AVR microcontroller to do serial communication in software, although keep in mind that depending on your application, this is really not what you should do. But I will then use this to contrast it to how you do it on the XMOS, because the XMOS architecture does not have any of these communication modules, so they're using quite a different approach to achieve the same thing, and we'll see how that can be potentially very flexible and useful. So let's say you have one of these AVR microcontrollers and you want to do serial I/O. This means that on some pin you want to output this kind of logic pattern. This starts with a start command and then you shift out your various bits. Typically that's 8 bits, and then you stop with the stop command. In particular, every bit that you send out has a pulse width. That is some time that you have to wait for until you send off the next bit. And I'm just going to call that delay. Of course, this delay depends on the baud rate at which you're sending out your data. So if you want to pull this off, you first define this delay, and then of course you define the transmit pin that you want to use to send out this data, and you set up that pin. I haven't shown that in my code, but in the end, at some point when you really want to send out that byte, you can use a function that might be similar to this one. This function receives 1 byte, and first you send off the start command. I haven't spelled that out in my code, but essentially that would just be pulling the line low and waiting for the delay. And then you enter this for loop. There is a variable I that starts at 0 and goes up to 7, and for each of these iterations you essentially write down the respective logic level to the port. That is, first I is 0, so you take the byte, you shift it to the right by 0 positions, so essentially it's the same byte still, and you mask it with a 1, and this will give you the least significant bit. Then you put this bit out to the wire, you wait for your delay, and you continue with the next iteration in which I would be 1. which means that you take the byte, you shift it to the right by 1, so whatever was in the second bit here now is in the first bit, and you mask it with the least significant bit. You write that to the line. And so on. You do this for every bit, and in the end you finish with the stop command. There is a bunch of problems with that. First, this is main code, so whenever you're executing this, your CPU cannot do anything else because it's busy doing that. Most importantly, it's most of the time busy waiting, and that might not make much sense. You could now argue that this is not the proper way of doing it. You could also use a timer interrupt and use a timer to interrupt and then send off each byte in the ISR. But then you're spending a lot of time in your ISR, so that entails quite a number of other problems. Or you might just use the timer to sort of queue your byte and then send it off whenever you have time, but maybe you just never have time, and even if you had time, you would then spend that time waiting for that delay to happen, so in the end you were stuck with the same problem. So let's have a look at how this is done with the XMOS, because as I said before, it's quite different. The XMOS has I/O ports that are quite flexible, which means that you can have buffered ports, and the ports also support serializing the data. This code here is an example of how you would do something very similar on an XMOS microcontroller. And I'll go through that real quick. First, you define a divider. This divider is used to divide a reference clock that's at least on the board I have, that's 100 megahertz. And this gives you then some clock rate at which you're shifting out your bits. Maybe there is no suitable divider because this has to be an integer, so there might be a baud rate at which you're not going to find a divider that gets you that baud rate. And in that instance, there is other ways to do this, but I decided to stick with this simple example here. This line here is quite interesting. This defines an output port that is buffered, which means that it's buffering essentially 32 bits. So you can write 32 bits in there, and they're going to be stored inside of the buffer and shifted out, as we'll see, at the clock rate that you define. The port itself is called TX out, and it corresponds to this hardware pin here, which is XS port 1E, and I'm going to talk about ports a little bit later. So you could just imagine this as some pin on the XMOS microcontroller. Then you define your clock, and you set the clock rate using the divider that I just discussed. And in the end, you tie the clock to the output port. And this tells the microcontroller to shift out the bits at the rate of the clock. In this case, I'm using an internal clock, but you could also use an input port as reference clock for your output port, and that would be handy in instances where you'd, for example, implement I2C, where you have to follow a reference clock that is applied to an input pin. So that all is setting up the port, and the very same UARTSend byte function that you call when you want to send a byte off to your serial port is this one. And what I'm doing here is I'm just taking the byte that I get here, and I write it to the output port. And everything else is done in hardware, that is, serializing the byte into bits and then shifting them out according to the clock. There is one particular advantage here, because this port is buffered. Not only does it buffer the byte that you want to send off, but because it's a 32-bit buffer, it can buffer up to 4 bytes without blocking. If you write more than 4 bytes into the buffer, this call here is going to block until there is an empty spot in the buffer to be filled up with the byte B. You might notice that this is not really standard C. There is this weird, like, lower than column kind of operator that is used to write things to the port, and there is also port column 32, which doesn't really look like standard C. And the reason for that is these guys came up with almost like a superset of C that allows you to exploit these kind of features. So if you have that, this is handy because you don't have to serialize it by yourself, as I did here. But you just can write your whole byte to the port, and serialization and also buffering takes place in hardware. But still, if you're writing out a lot of data, then in the end you're going to fill your buffer and you have to block. And then you're still in the same situation as before. You essentially have to spend time inside this function here instead of doing other cool stuff on your microcontroller. Which brings me to the nature of this microcontroller, of having multiple cores in which you can do things in parallel. In the beginning, I had some issues grasping the key concepts of the Xcore architecture. And in my opinion, the reason for that is that they're sort of using quite an unusual terminology. They use terms like tile and logical core, and I think it's worth spending some time in discussing that to really understand what you can do inside these chips. On the sketch, on this sheet of paper, there is really 2 blocks, and they refer to these blocks as tiles. There is quite a bunch of things inside these tiles. For example, there is hardware related to the port, there is dedicated RAM here, and there is also the ability to connect several tiles together using these links here. And you can see that this is reflected for each tile, so there is also RAM up there that is specific to this tile. Now, you can think of a tile as, I guess the usual normal term that you use for that is core. So this is sort of one CPU that runs at a specific clock rate and runs code, essentially. But inside each tile, there is a number of what they call logical core. And I would refer to that as hardware thread. And we're going to talk in a second about the difference between a hardware and a software thread. But essentially, for the chip on the StartKit, there is 2 tiles, as shown here. And in each tile, there is 8 logical cores. So what is a logical core, or as I call it, a hardware thread? You might know that when you're trying to run things in parallel on a computer, most of the time it doesn't really run in parallel. It's just that things get executed and then interrupted, and some other things get executed, and these switches between the different contexts are so fast that it appears as if it were running in parallel. And they do exactly the same with these logical cores, with one exception. If you do this in software, you need a scheduler that really makes some overhead in switching the context from one thread to the other. Because there is registers that you have to swap out and fill in some other things to set the stage for the other thread for it to run properly. And in this chip, the hardware threads, or the logical cores as they call it, there is no large overhead required to switch between them, because, for example, all the registers are replicated for each logical core. So you need a scheduler that stops one core and tells another core to run, so you don't have sort of this multiplication effect of more clock cycles available with each logical core. But the context switch is really minimal. So this is what the key concept is. And in the end, you can use this, for example, to run the UART command that I showed before on one logical core, and something else, some calculation maybe, some DSP stuff on another logical core. Of course, the amount of clock cycles that you have available is distributed among all of these cores, but still you have the guarantee of some amount of clock cycles available, and you don't lose anything when you have to switch between them, because this is done in hardware. In terms of documentation, there is sort of good and bad news. On the bright side, they have really a substantial, quite extensive library of documentation. This includes hardware schematic, datasheets, example applications, introductions to their library that you can use to program the chip, and all of these kinds of things. So that's really nice. There is one problem with that though. This library is quite fragmented, and it's really hard to find information with respect to whatever you're interested in right now. In particular, one thing they do is when you install the software, the first thing they tell you is to have a look at their sample code for blinking LEDs and whatever. That is, however, not the way, at least for me, things work out nicely. What I prefer to do is I'd like to have a set of documentation that tells me some things about the chip and how to use it and what its capability are and things like that. And when I went through that documentation, I can start look at the code and understand the syntax and understand what the code is doing and what kind of approach they chose to do whatever the code is doing. So I will link in down below a couple of particular documents that got me started. This will include the hardware manual to the StartKit itself that contains a schematic and also various information on the port. It will include a reference to the library that you can use to program the chip. It will also include an introduction to this XC programming language that really is, it's almost like C++, some additional things that make a thread handling and port I/O easier. And then on the website you will find a lot of they call this soft IP, which really is a pre-programmed module that you can use, for example, to implement a serial COM module or I2C, I2S, and they have quite a lot of these modules, which makes things really easy if you want to get started, because then you don't have to implement all of that yourself. So in a way you can think of that as some sort of, it's almost like an Arduino library. It's just that this does not use sort of these hardware modules that are inside the chip on the Arduino, but it's rather all done using their threading approach and their flexible port I/O. Let's talk about this table that I printed out here though, because this is from their StartKit hardware manual and it shows how to use ports. In particular, they have as opposed to the Arduino, where every port is an 8-bit port, although you don't realize that. The thing with the AVR chip is it's an 8-bit microcontroller. So if you want to, let's say, change the logic value on one pin, what you have to do is you have to take the whole port, which consists of 8 pins, and you have to read that, change 1-bit value, and write it back. If you do this on the Arduino, it sort of gets abstracted, because this digital write function does really just exactly that. So anyway, as opposed to that, they have various bit sizes for the ports. There is 32-bit ports, 8-bit ports, 4-bit ports, and 1-bit ports. And in fact, the pin I used in the previous example with my UART code was a 1-bit port. So this means that all you can do is you can write stuff to that port, and if it gets serialized, then it's either logic high or logic low. But you could, for example, also have a 32-bit port and write a 32-bit integer to that. And that would change the values of all the pins, the 32 pins of that port, all together in one step. Or you could have an 8-bit port, but buffer it with 32 bits, which means that the stuff that you're writing to that port is chopped into 8-bit pieces and shifted out in parallel in chunks of 8 bits. And the reason I'm highlighting this is I found this to be quite confusing. If you look at this table, for example, there is here a pin called X0D11. And you can see that this is a 1-bit port called 1D, But there is a bunch of other things. It also tells you where you find this thing on the board, and that this is a MOSI pin, and this is where things really get confused, and I actually spent a lot of time because I got confused because of that. So if you look at that X0D11 pin, you find that on the board here. It's this guy here. This is nicely labeled on the silk screen with X0D11, so that's all nice. But it says MOSI next to it, and if you turn the board around on the silk screen, you will find that there is actually a MISO label to this. So this is really confusing because in the end, this MOSI here refers to how this is hooked up to the SPI flash chip on the board, and doesn't have anything to do either with the Raspberry Pi connector or with the function itself, because you can essentially pick any 1-bit port, or if you want to do tricks, also 8-bit or other ports to do that. But this is in any way a table that I found very important, and I printed it out and hung it up, because you always have to first decide what kind of port you want to use. If you want to use a 1-bit port, then let's say, for example, 1E, you have to check what pin that corresponds to, and then find that pin on the board. So this is this could be easier if they had macros for various things, and also all the labels on the board itself. But in any case, once you get used to that, it's fairly straightforward. You just have to understand the concept of this port map. Okay, I hope you found that interesting. As I said before, the next video in this series is going to be a hands-on experiment where I will drive one of these LED strips using this StartKit evaluation board. In case you're confused with all of this tile business and cores and hardware threads, I recommend you watch that once it gets out, because I'm sure then things will become much clearer. And also, because that project involves a lot of LEDs, I'm sure it's worth watching, because whenever you have LEDs, things are going to be awesome and cool. So I really hope you're going to stay tuned for that one. Thank you very much, and goodbye.